Thanks, William. Yes, okay. So yes, joining us today is Taicheng Huang. So Taicheng and I would join our old lab in the same year, and we were lab mates for 3 years. But now she already got his PhD, and I'm still working on it. But yeah, before giving you a more detailed introduction of Taicheng's background and his amazing CV, I just want to, and William already expressed our thanks for him to join us, but I just want to express that again, because on the one hand, I feel bad because when I sent the invitation, I know it's midnight in China, but on the other hand, I feel it's just excited to hear his cool work. And so Taicheng is a postdoc at Tsinghua Laboratory of Brain and Intelligence, and he is also selected as Shuimu Tsinghua Scholar, which is a very prestigious and competitive postdoc program in China. And he got his doctoral degree at State Key Laboratory of Cognitive Neuroscience and Learning at Beijing Normal University in the past summer. And he has a very strong background in both computational neuroimaging, computational modeling and cognitive neuroscience. And his research combined neuroimaging in fMRI in particular and artificial intelligence to understand the neuromechanism of object recognition. And when he's not busy doing science, Taicheng enjoys trying out different restaurants. And he told me that he has tried almost all nearby dining places around Tsinghua University, which I really envy that. I haven't go back for 2 years to try different restaurants. Yeah, and so please join me welcoming Taicheng.
Thank you. So now I will start my my talk about today's presentation. So my name is Taicheng Huang, and today I'd like to show you research about the mechanisms of object recognition, and we want to design some new paradigms and some new modeling method to help us understand the mechanisms of object recognition. So the title of today's presentation is a finding that we find that the real world size of objects serves as an axis of object space. And I'd like to introduce you why we think this idea about object space as a potential mechanism of object recognition. Okay. First of all, as we know that the recognition ability is a very important and critical ability for us to live in this world, and also it is a window to us to learn the world. So as I show you two different figures here, the first one is a natural environment, and the second one is a city environment, and we can very easily to identify objects within each figure, such as trees or buildings. So this ability is so common to us. However, until now, we are still unclear to the mechanisms of object recognition. So to understand the mechanisms of object recognition, perhaps we need to know what is the keyword of the object recognition and what do we do by using the object recognition. So according to the ideas from James DiCarlo, he gives us a concept that the core recognition includes the rapid and highly accurate object recognition. So the keyword perhaps in the object recognition is rapid and accurate. So we can follow this idea for some further analysis. So let's start with the strategy as a mechanisms of object recognition. That is, we can first do feature extraction and then do feature integration. So by using feature extraction, we can extract the different features from the object and we can collect information from it. And then we need to integrate different information to help us make a decision, and we can get a category about one object. So this strategy is very common to us. For example, as you can see here, it is a computer screen. And if we follow in this strategy, we can first extract different features, such as its color feature, its texture feature, or until to the orientation feature. And we can further integrate this different feature and get to know this is a computer screen, but not an animal or a dog. So it is very normal to us. However, this strategy has its limitation. So the limitation is that in our real world, the physical world, to each object, they have unlimited features in unlimited features. The features are listed above is some potential possibilities, but we can still list more features, such as an example, this object consists of atoms. So atoms is another feature, but it's a very trivial feature. But it's a very trivial feature. So in our real world side, in our real world, so we need to process unlimited features in an object. However, in our psychological world, we only have very limited time and limited resource to process different features. So this contradiction between the physical world to the psychological world make it impossible to just use the strategy of feature extraction to feature integration for us to do the object recognition. This is only one object. So if we focus on our daily life, we need to see many different objects. So different objects, they also have their relationships. So we also need to process more information between objects. So this makes it, we need to find out something more within the strategy for us to do object recognition. So my opinion is that perhaps one prerequisite of object recognition is that we do not extract every single feature from the object. We just need to find a way to extract a few critical features to finish our object recognition mechanism, object recognition process. So if we actually need to extract a few critical features, how do we extract a few critical features is another question, and the next question to us. So here in this question we also have two keywords. The first one is few, and another one is the critical features. So let me first clarify what is the critical features. Actually, we can distinguish critical features from another feature that is the trivial feature, such as the critical feature means something important to us, especially to our daily life. However, the trivial feature is not such kind of critical things. So, for example, the atoms is not a critical feature because it is meaningless to our daily life. So we can have a starting point by focus on the keyword of critical features, or the keyword of few. So the first starting point is that we can define what is a critical feature. The critical feature should be interpretable and meaningful to us, and also highly related to our daily life. So this critical feature makes us understand the world. So my opinion is that we can, this starting point can help us satisfy the accurate requirement. So following the starting point one, what is the critical feature? Actually, every embodied features, which is highly related to our daily life, it perhaps several critical features for us to do the object recognition process, such as the real world sites. And another starting point is that how do we solve the problems of few? So the starting point require us to use limited critical features to encode enough information from the outside world. So that means the critical features should be independent from each other, so to maximally reduce redundancy. So this requirement this starting point help us satisfy the rapid requirement. And following the starting point two, I can introduce you the object space, the concept of object space. As you can see that we have, in object space, each object could be represented by different axes, and each axis was independent from each other. So they can maximally encode enough information from the outside world. And for each axis, they could be represented by different critical feature, or what I say here is the embodied feature. So we can have this hypothesis to answer the mechanisms of object recognition. So this looks very good, but we also need to answer the below question, that is, does object space exist in our brain? If we can find some clues in our brain, so we could make the object space as a starting point for us to finally answer the question of mechanisms of object recognition. So actually, there are several evidence that link object space to the object recognition, such as the first evidence was published in 2020. Bao and his colleague found that in macaques' occipital temporal cortex, the regions could be separated by two axes into 4 different clusters. The first axis is the curvature axis, which shifted from the stubby to spiky. And the other axis is the animal C axis, so which shifted from the animal to artifact. So to human studies, we can also find several evidence as this evidence found that the animal C and the real world size could be 2 potential axes. So this evidence help us link the object space to object recognition. So actually, if we want to link the relationship between axes in object space and object recognition, what we should do to pass the most restriction is to examine it in sufficient requirement and necessity requirement. So here we have 2 directions. The first direction is that if we have a good object recognition ability, so that the object recognition ability help us form several axes in object space. So this is the sensitivity criterion. And in the other direction, that we need to satisfy the necessity criterion. That means the axis in object space should support the object recognition ability. So this is another criterion. And some traditional biological study can support this, the sensitivity criteria. That is for human and macaque, we have good object recognition, and we have said that we form an object space in our mind. And what we can do is to find evidence that encode such as the size information, which could be play a role as the axis in object space. And if we want to examine the necessity criterion, so the size, we need to do the following procedure. That is, the size axis in object space should support the object recognition. That means if we remove one size axis in object space, so the object recognition should be decreased. So furthermore, if another criterion I listed here is that the independence criterion, because I mentioned the object space hypothesis. So in object space, different axes were independent from each other, so to maximally reduce redundancy of outside information. So as you can clearly find that in traditional biological study, there are dilemma. The dilemma is the manipulation question. So traditional biological study can help us verify the sensitivity criterion, but they cannot help us verify the independence criterion and the necessity criterion. That's due to we cannot directly manipulate axes in object space, so to verify the decreasement of object recognition ability. So it looks that we need to find some new method to overcome this dilemma. Here I use a deep convolutional networks which we use as a substitute to primates ventral visual pathway. So I think we use this platform to overcome the manipulation dilemma. As you can see here, the deep convolutional network can extract information from different images, and it can extract a lot of features from this image. And finally, it can integrate different features together to give us output. So many studies found that the DCNNs have good consistency as primates ventral visual pathway. And as you can see, since 2020, 2010, the error rate of DCN decreased a lot until to 2014. It achieved very similar error rate as humans. And most important thing is that the DCN is human designed. So it is totally manipulable to us. No matter its stimuli or learning rules or architecture are totally manipulable to us. So this makes us possible and feasible to direct examine the two criteria, the independence criterion and the necessity criterion. So in this study, I would like to explore if real-world sets of objects serves as an axis of object space. And we would like to use a mutually inspired paradigm. The mutually inspired paradigm includes the computational modeling, that is the DCNNs, and also we want to verify some results in biological observation, that is the fMRI techniques. So here is the outline of today's talk. And firstly, I will demonstrate the most important question, that whether it is true real-world sets serves as an axis of object space. And I would demonstrate it from sensitivity criterion, independence criterion, and necessity criterion. And after I demonstrate this hypothesis, and we can find a set axis in object space. So we can further answer another question, is how is the set axis formed? And I firstly also use the DCNNs to explore some potential factors. And further, we can get some potential factors. I can verify these potential factors in humans using the fMRI experiment. And I find some some consistency and some difference. So I will further give an inspiration analysis to figure out how to improve our DCNNs by comparing with humans data. And finally, I will give you a brief discussion about today's talk. So firstly, in this study, I would like to firstly show you the dataset. Actually, the dataset we use is an image dataset with real-world sets of objects. So the dataset was downloaded from Talia Concourse Lab, who is a pioneer to do to study the properties of real-world sets in our brain. And the dataset includes 100 background-free single object images, as you can see on the right side. And to each image, we can measure its real-world size. And the measurement follow the we make the following procedure. As you can see here, it's an object, and we can get its bounding box. And the object set was measured as the diagonal length of it. So to each object, we can get their object size. So we can get 100 object size values from this data set. And also, I grouped the 100 objects together according to their real-world size. And we get 8 groups, and at least for each group, we have 6 objects. The reason why we do this is to remove such unrelated factors, which I will explain it more in next slides. And first, I would like to examine the first criterion, the sensitivity criterion. And my question is it true that the DCNNs with good object recognition ability can also encode real-world sets of objects? So to answer this question, we first need to build an ideal observer model. So this ideal observer model could be deemed as a golden standard to us. And we have a very basic ideal. So if one DCN have a good which have good object recognition could also encode size information. So objects with similar size can active DCNs to form similar representations. So as you can see here, I show you the eight groups here, 8 objects in 8 groups here. So to just within some groups with similar real-world size, their similarity were larger than objects from groups with different real-world size. So as you can see here. And we can get a representational similarity matrix as shown here. So this representational similarity matrix, the diagonal of it, for each element which is more closer to the diagonal line, it will have larger similarity, and for element which is far away from the diagonal, it will have smaller similarity. Okay, now we get an ideal observer model, and we can further use this ideal observer model to examine our hypothesis. So we further need to calculate the representational similarity of objects' real-world sets in DCNNs. And I perform the following procedure. As you can see here is a pre-trained DCNNs. Here I show you an AlexNet, and the pre-trained DCNNs is perform very good object recognition ability as humans. And we can input different images here. As an example, I show you one image from the real-world size dataset, and I put it to the pre-trained DCNNs. And we can extract activation array from it, from all of its layers. And the activation array indicated many different features, such as the color features, or shape features, or texture features, or size features, or perhaps we have size features. So to some other objects, we can also do the same thing. And to objects within the same group, and we can average all activation arrays together. And the average method can help us remove all confounding factors which is unrelated to the real-world size of object. So we can finally get a set-specific array, as you can see here.
I have a question here.
Okay.
For example, for a certain layer, you have 100 nodes. And so 100 nodes corresponds to 100 features. So each image you can get a vector includes 100 features, and you just average the value of each value in that vectors.
Yeah.
But I think, for example, different nodes will respond to different objects maybe.
Okay.
And here you just average the activation in each layer. I think it's not a very good method here. Okay.
Actually, this is the thing that could be discussed further, because I cannot accept the idea that each node encode one feature, because to deep convolutional network, it can extract features from the outside, and for each node in higher layers, it can achieve get feature from lower layer, from a lot of lower layers, from a lot of nodes in lower layers. So to one node in the higher layers, it can get many different features. So for each node, it is not specific to one feature.
I mean, for example, a node is sensitive to the color, maybe to the red color, and one of the object is red, and so the value of that node is high. And the object is maybe blue, and the value of that node will be low, and you average the two values, so you will not see the activation of this node.
Okay, we further have a result can support my opinion, and your question could be answered at least that we group at least 6 objects which have different colors. So if one, for example, to the bottom it has the red color. So to some other objects they have different colors. So 6 objects is enough to us to average the color information from
Okay, so here you average the values, so ignore the other features instead of the size, right?
Yeah, we have a hypothesis that if objects with different features, which is unrelated to real world size, so the activation array can encode different information, such as one array specific to right button, so it can encode the right information, and some array can also encode the blue information. And the red information and blue information may have different directions. So when we average them, so we can remove their information, their confounding factors.
Okay, I understand.
So this is our hypothesis, but further you can see a result in untrained AlexNet, and you can find this balance is a very good balance, and we cannot get the similar matrix as the original AlexNet.
Okay, I have another simple question. The retrained DCN here means the DCN is trained on ImageNet, or
ImageNet.
The dataset you use, the big size and small size.
Yes, the dataset is also an image dataset. So the AlexNet was trained on the ImageNet dataset, which includes more than 1 million
I understand. My question is, did you also train on the dataset?
No, I didn't train another AlexNet by using the real world size, and I didn't do fine tuning to the original AlexNet. This AlexNet is a pre-trained AlexNet, which can be downloaded from the PyTorch website.
Yeah, I understand.
Okay.
Thank you.
Okay. So we can get a specific activation array, and to some different objects within different groups, we can do the similar things, and we can also get the sets information, get the set activation array. And what we should do is to calculate the representational similarity between different groups, because for each group it represents as one set rank. And we can get a representational similarity matrix as shown here. And what we should further do is to compare this representational similarity matrix to our ideal observer. So our results found that in convolutional 4-layer, the AlexNet convolutional 4-layer, we can find a very similar representational similarity as the ideal observer, and you can find their correlation are very high. This is a controlled analysis, and we also do the same procedure in untrained AlexNet, which shows no object recognition ability. And this result found that for untrained AlexNet, its convolutional 4-layer do not show something like the ideal observer. And we also do the similar procedure to different DCNNs architecture, such as the VGG families, retina families, and the exception families. We also get the similar result. So all of these results suggest that the DCNN for object recognition can also encode the real-world sets of objects. So we further need to verify different independent criteria. That is, does the size axis exist in object space? So to answer this question, we need to recover one object space here. So the way for us to recover an object space in DCNN is to using a large amount of images. We use 50,000 natural images, which includes a large amount of features, different features, such as the color features or some shape features. We do not care the specific features, but they include enough information so they can cover a large space. And we input all of these images into the AlexNet, and we can extract their activation in convolutional 4-layer, and we can get a matrix of the activations. And we can use the principal component analysis, the PCA, to get the transformation between the original activation to the principal component. So the transformation function is a different axis. So for each axis, they are independent from each other. So until now, we can recover an object space, and we would like to use this object space to examine if an axis is specialized to real-world sites, but independent, of course, it independent of others. So our way is that we can use the real-world site dataset and input the 100 dataset images into the AlexNet, and we can get activation array, activation matrix, and we project the activation arrays into our previously object space, and we can get 50 pre-simple components. So if we want to examine whether an axis is specialized to real-world sites, so we can do an impairment analysis. So that means we can separately remove each principal component to get impaired activations. And we can further do similar things to get impaired representational similarity matrix. So the representational similarity matrix could be, their correspondence to the ideal observer could be measured. And we can compare it with the original representational similarity matrix. So the decreasement could be measured as a specialization of an axis, whether there is an axis is specialized to real-world sites. So we can directly measure the effect with this metric. And our result found that we only found one axis, that is the second axis, show very good specialization to the real-world sites, but not to other axes. So if we compare it with the untrained AlexNet, we cannot see any axis that is specialized to the real-world sites of objects. So if we focus on the representational similarity and the impaired representational similarity, we can see they have very large difference. So that means we verify the independent criterion, that is the real-world size of objects serves as an axis of object space. And since we find one size axis in the object space, so we can further quantitatively examine the quantitative relationship between the size axis and the actual size, the real-world size of objects. So our way is to build a function, a mapping between the real-world size of object and the PC2. So we can, the function could be defined as different relations, such as the square relation and the cube or linear, square root, cube root, and the logarithm. And the fitness indicated the most potentially quantitation relationship between the PC2 and the real-world size. And our result found that the PC2 and the real-world size could mostly show a logarithm relationship. And further, I show you here the scatter plot, and the x-axis is PC2 and the y-axis is the real-world set of objects after the logarithm transformation, and we can see a very good linear relationship. So this result also follows the Representational law, which is consistent to human beings. So finally, we need to verify another criterion, the necessity criterion. So if we want to verify this criterion, what we should do is to manipulate the size axis and to examine whether the size axis supports object recognition. So we can remove the size axis and examine the object recognition ability, whether the object recognition ability will be impaired significantly. So our result found that if we remove the size axis, the prediction accuracy for object recognition decreased a lot. But the effect size is not very high, but it's still significant. And if we if we focus on the 1,000 categories, and we find that more than 600 categories show impairment of object recognition. So that suggests the necessity criteria that its size axis also support object recognition. So All of these results could be also replicated in other deep convolutional network architectures. As you can see here, all results are consistent to different architectures. So until now, we verified the hypothesis of real-world sets, so as an axis of object space from the sensitivity criterion, independence criterion, and the necessity criterion. And we get one set axis. And the next section, I would like to examine how is the set axis formed. And the first step for me is to explore the potential possibilities that will affect the set axis in deep convolutional networks. And I list several potential possibilities to which may affect the formation of the set axis. The first one is the retinal size difference between objects. As you can see, one potential is that if we want to measure the size difference between different objects, perhaps within one object, within one images, that different objects have different retinal size, such as in this image, the human is smaller than a cab, and the cab is smaller than the building. So these relations may transfer into two different images, which we may tell the deep convolutional network to encode, have the information to encode the size information. So what we can do is to remove all background of it to get a single object image and retrain the retrain the AlexNet, and also do a similar procedure and to examine whether we can still find one set axis in the new trained single object, new trained AlexNet. Okay, this is the first potential possibility. And the second potential possibility is a task demand for categorization. So the idea is that actually we can categorize one object as different objects, such as we can label it the image as a cab. So it will have the same concept as another images with a cab, but we can also label it as an artifact. So it will be the same object as a barrel. So because both of them are artifacts. So the task demand for categorization could be another potential possibility for the image for the AlexNet to form the set axis. And the third one is that it's intrinsic factors of objects, such as the shape information and texture information. So perhaps we use shape information to help us do to distinguish real-world sets of objects, or use the textual information to distinguish the sets of different objects. So these are three different potential possibilities. And first, I will show you the result of the retinal size difference between objects. And our result found that if we retrain AlexNet with just a single object image, it can still show us the size axis, as you can see here. And it still show very good linear relationship between the PC2 values and the real-world sets after the transformation of logarithm. And so that means the retinal size difference among objects is not the main possibility to form the size axis in DCNNs. And we also examine this possibility by examining whether the size axis has a tolerance to the retinal size of objects. So we do the following method. That is, we narrow the image, the original images into as different proportions. We use three different proportions: the 70% proportion and the 50, and is 20% of its original retinal size. So we can do the same analysis as previously, and we can build a relationship between the PC2 value and the real-world size. And as you can see, the size axis has a very good tolerance to retinal size of objects. So this further indicated that the size axis is shows little or even no relations with the retinal size of objects. Another potential possibility is that perhaps the task demand for categorization could affect the formation of real size axis. And we do the similar things, and we retrain a new DCNNs with just 2 labels, and we ask the DCNN to distinguish one object as an artifact or as a living thing. So this will largely decrease the fineness of its ability to distinguish different objects. So our result also shows that we can still find one size axis in the DCNs. So that means the task demand for categorization is not a main factors for the formation of the size axis in object space. And finally, we investigate the intrinsic factors of whether the intrinsic factor can affect the formation of the size axis. And we separately examine the shape information or texture information or no information to our hypothesis. And you can find that the DCNN can use both shape information and text information to encode the real world size. However, if the images contains no shape or textual information, if we shuffle them, the PC2 value do not show good correlations to the real world size. So this suggests that the DCNN use both shape and texture to represent object size. And now we get two potential factors which may affect the formation of the size axis in object space. And we further want to verify these potentials in humans using a fMRI experiment. And to verify this, we recruit 10 adults, whose age was ranged from 18 to 27. And we asked the subjects to do the following experiment. So the experiment is a block design, which for each run, it includes 4 block size. And to each block size, we include 3 different conditions. And so that means 2 block size include all 6 conditions. And the 6 conditions include 2 original images, silhouette images, and texture images with large and small size. So we have 6 conditions here. So the rest 2 block size, we counterbalance the first 2 block size. So 2 block size. So we can get this experiment design. And for each object, for each subject, they perform 4 runs in total. And we can correct the board signal for each subject. And we further do a univariate analysis, as you can see here. And we measure whether in original condition, in silhouette condition, or in textual condition, there is a size difference. So our result firstly replicate the result published by Conquer in 2020. We replicated their results, and we further investigate the silhouette condition and the texture condition, and we can find that human only use the shape information but not the texture information to encode the size information, to encode the object size. And we use ROI analysis to extract the average magnitude, and we can also get a similar result that humans do not use shape, do not use the textual information to encode object size. So we further use a multivariate analysis examine whether the border signal could help us to from the occipital temporal cortex could help us to decode the big object and the small object. So we use a linear support vector machine and with linear leave one out cross validation to do a categorization. And our classification found that to the border signal that if signals from the original condition or the security condition, they can be successfully encode the big and the small objects. But to signals from the texture, they cannot encode the size information. And we also did this analysis by using a searchlight analysis, and we can only find the result in occipital temporal cortex and in the original and the security condition, but not in the texture condition. All of the above results from fMRI experiment suggested that humans can only use shape information to represent real-world sets of objects, which shows the inconsistency to the deep convolutional neural networks. So this makes us to think about the reason, and we give a hypothesis that is whether texture is also necessary for a DCN to form a set axis of object space. That means perhaps the DCN that trained using enough information, enough images that both have texture bias or shape bias, make it need to use texture or shape information to form a set axis and do its object recognition. So we want to verify this question. And to answer this question, we use a stylized AlexNet, which trained with transferred images, as you can see here. So the transfer image was generated from the GAN. So that is a generative adversary neural network, which can form different stylized images, as you can see here. On the left side, it is an original image, and on the right side, we generated 6 different images. And to all of these images, they retain the shape information, but confuse the texture information. So the DCN, which trained with the transferred images, may not sensitivity to the texture information. So we further examine this result by using the previously procedure, and you can see the stylized AlexNet can still show good consistent correspondence to the ideal observer, and also it can show one set axis compared to some other axis here. And we also find that this stylized AlexNet is sensitive to the original and the shape information, but not sensitive to the texture and the shuffle information, as you can see here. So here is all of my results. And I would like to make a brief discussion. So the first one is that the importance of real-world sets in object recognition. So why do we think that real-world sets is important? Let's not do just because of it is embodied features. So we made 2 different reasons. The first reason is that the real-world sets can help us determine the layout of objects in the real world. As you can see here, it is a very normal configuration to you because the small size objects will press above to the large object. So it is very normal to us. However, to another configuration, it is very weird to us. So that means to these very weird objects, we may need to devote more attention to it. That can help us to survival in our daily life. However, to some normal configurations, we do not need to devote enough attention, but we can think that that is very normal. So it ascertain our survival in the world. And another importance is that the real world size in objects of objects can help us determine our interactions to objects in the real world side in the real world. So it directly relates to affordance, such as for big objects we can define different actions, such as held, lifted, or raised. However, to small objects we can only pinch the or grip the or grasp these different objects. So that means to a real car, what we can do is just sit in the car, but we cannot hold a car. However, to a toy car, so what we can do is to grasp the toy car. So the different operations for us to do different objects make us get different categories of the object. So it can help us to do object recognition. So these are two important factors that I think why real world sets should be considered in object recognition. So we further get a conclusion that the vision is not just for perception, but it's also for action. So another discussion I would like to say is that why texture is not important for us to infer real world sets of objects. So my idea is that the texture is easy to be influenced by environment. So that is not invariant to us. So for example, as you can see, here are four different dogs. They have very similar shape, but they have different texture, and they are in different environment. So however, we can still identify them and know they are dogs. And if we just see the security images as a dog and a cat, although they both shows very similar shape, but we can still recognize them. So that means the shape information is invariant, but texture information is not invariant. So it is easy to be influenced by environment. So finally, here is my conclusion and the take-home message. So first of all, we found that real-world sets of objects serves as an axis of object space for object recognition. And the second is that the set axis is formed from the intrinsic features of objects. And finally, we use a mutually inspired paradigm of computational modeling and biological observation. We found that the textual feature of objects looks unnecessary for us to represent real-world sets of objects. So that's all. Thank you for your listening. And if you have any questions, please raise your question. Thank you.
Thank you, Taicheng. Yes, thanking him for wonderful talk. That was fantastic. Yes, we have time for a couple questions here.
I think this talk is over. Wait.
We have time for a couple questions if anyone would like to raise them.
Okay. Yeah.
Hi, I have a question.
Okay.
So related to textures, what are your thoughts on like text forms from the Conca lab? If you're familiar with them.
Familiar with them? What? Excuse me.
Like the Conca lab's done stuff with mid-level features, like they take big and small objects and they distort it so that it's difficult to tell what it is, but it retains mid-level features like texture primarily. And they show that when you do fMRI on these weird text form images, that you get results similar to the original paper that you're referencing from 2012.
Yes.
Like my impression of that was that then texture is probably important to like real world object size, but your results are saying that texture is maybe not important. So I was wondering what your thoughts might be on that.
Yes. Okay. This is a very good question. we think about this question before. That my opinion is that in Conquer's study they use a kind of stimuli, but still keep a little shape information. And they mentioned that in their mid-level images still contains very little shape information, but retain a lot of textual information. So my opinion is that perhaps the rest shape information they use in their images may make their results from that the human use mid-level information to do the sets distinguish. Okay.
I have a quick question about the specifications of the network that you use. So I don't do convolutional neural network stuff, but my understanding is that you can kind of arbitrarily pick the number of layers, and what layer you look at in terms of the representation is really important for what kinds of features it might represent. So my question is kind of, I guess I kind of have two of them. One is, how many layers are there in this in the network that you use, and how did you decide on the layer that you chose to be what you think is representative of object size? Okay, thank you. Actually, we did an analysis to every layers, so to every architectures. So here I show you one result. This is the AlexNet result. So the picture I show you in my presentation is a convolutional 4-layer because it shows the largest similar consistency to the ideal observer. And our result found that since a convolutional 2-layer until to the FC 3-layer, and they all show very good correlations to the ideal observer. And to different architectures, we also do the similar things, and we just measure, we just show the results with the largest correspondence to the ideal observer. That's because too many neural network, they have a lot of convolutional layers. So it is very hard for us to show every result of every layers here. So we only show the result of AlexNet in the 8 layers, the result of 8 layers here. Okay, thank you. Okay.
All right, it is 2 o'clock now. I want to thank our speaker. I know it is staying up for so late with us to give us this wonderful talk. One more virtual round of applause for our speaker. Thank you so much.
Okay.
And yeah, I sent out the preprint with our announcement for the talk, but I'm sure if you'd like to give out your email, if you'll have further questions, you can contact that way. Yeah, there it is.
Yes, if you are interested with my research, and you can contact me with any questions or any comments. So thank you.
Well, yeah, thank you all for coming. We look forward to seeing you at the next workshop.
Okay. Bye-bye.